Good afternoon, Black Hat. Thanks for being here. Obligatory background slide. If you don't know me, I work for Google on the Project Zero research team, specializing in Windows, mainly privilege escalation sort of vulnerabilities, mainly because I like logical vulnerabilities and rather than memory corruption. So I find that quite often in these sort of types of things. So what exactly am I going to talk about? So this will be quite a technical talk. It's a talk for people who want to hunt for bugs in the Windows kernel. And it's specifically related to the Windows security, access security mechanisms, and how it relates to how kernel code and kernel drivers may actually interact with the Windows security mechanism to verify a user's identity. Now, Windows is actually a reasonably complicated sort of security architecture, but you can actually sort of break it down to sort of three main parts. The first part is each resource, say a file or a process, has some sort of security associated with it, which defines who is allowed to access it and what they're allowed to do once they do access it. This is stored in something called a security descriptor and contains various bits of information about the securable resource and what you're allowed to do with it. The next component is the process, and specifically its associated access token. And the access token is your user identity, effectively. It provides the identity to the operating system. And these two combine when you do system calls or other kernel and driver code gets involved and talks to something called the security reference monitor. And the security reference monitor is responsible for actually enforcing the security of the system and providing security decisions. So you can find documentation about the SRM, the security reference monitor. Basically, if you're doing kernel mode code, if the function starts with the prefix SE, that means it's something related to security. Now, the real core of pretty much all security decisions is the access check, and this is done usually through a function called SE access check. And effectively, it's just sort of taking your token and applying it to your security descriptor and making a decision on whether I'm going to give you access or not. So there's a few different steps. The first step being checking what is called the integrity level. And the integrity level is something they added in Vista, which it's like a mandatory access control mechanism. It's simply a number. Your access token has a number. The resource has a number. And if you are above or equal to the resource number, you're allowed access. Otherwise, it can tell you to go away. Then it goes into things like owner check. But then the DACL check is the most important part. This is where it determines what you can actually do with that resource. If that succeeds, you've got access. If it doesn't, it'll tell you to go away. Now, the access token is actually a pretty complicated structure. So if you think of a sort of traditional Unix system, you may have had user IDs or group IDs, just sort of simple numeric values. But the access token in Windows uses something called the security identifier, which is actually a sort of more complicated structure. This is this S and multiple sort of numbers after it. Now, it also contains things like your groups. So you have your user, it has your groups. It has your mandatory label. This is your integrity level. And it also has privileges, which I'll go into a little bit briefly at the end because it has important consequences elsewhere. But fundamentally, your access token is just another kernel object. It's just another allocated buffer in memory, allocated structure in kernel memory, which has some values in it. And obviously it has then a similar association with all other sort of types of kernel objects, including it can actually be securable. It can have its own security descriptor and access control list, and which defines who can access that token information. Now, it wouldn't be, obviously, it's too simple if it was just a single type of token, because obviously there's many sort of scenarios in which you may find yourself. So I've kind of broken this down into sort of four main types of tokens. You could probably argue for different sort of categorization. But the sort of main one you would normally see, the normal token, is just the one you would run as a normal user. You'd have your normal basic token. Now, when you get UAC involved, user account control, you may also have something called a linked token. And this is just another token which is associated with the same token. So for example, you could have an administrator token linked to your normal user token, and potentially you can switch between them by talking to the appropriate service. Now underneath normal tokens, you have two system calls which allow you to create sort of new tokens with new security properties. You have first NT-filter token. This creates what is called a filter token, and you actually also see this referred to as a restricted token because of the Win32 API calls it the create restricted token. Now in Windows 8, to support app containers and the sort of immersive applications, a new type of token was created, the lowbox token, and then as an appropriate function to call. But both of those functions take an existing token and effectively copy some of its security information and imply new sort of security categorizations. So there's loads of important fields you need to bear in mind when sort of thinking about token security. Obviously, you've got your groups, your user, but you also got things like your token ID, which is a unique 64-bit number. It's basically an incrementing number which is assigned to each token. It's only locally unique, but that's all that matters. Counterpart to that, you have the parent token ID, and this is used sometimes for security decisions, and just reflects, say, when you're doing a filtered token, reflects which token you created that token from. And then various other sort of things in there. Now, in common with all kernel objects, or pretty much all kernel objects, you can actually access it from user mode. There are system calls to get hold of access tokens and manipulate them. So when you do that, you get hold of a handle